We want to start this part by asking a question. Is Gauss's law always valid? As we said before, Gauss's law is always valid. Always valid meaning that it's always valid no matter how the charges are moving in space, if they're at rest or moving or any arbitrary way. Gauss's law is always correct. There's another question we can ask. Can we use Gauss's law only to derive the electric field of any charge distribution? The answer to that question is not always. So those two questions are not exactly the same. Let's see why this is the case. If you take an arbitrary charge distribution that doesn't have any particular symmetry, you won't be able to find or make a Gaussian surface that will allow you to calculate the electric field. Now the reason is, remember, the integration of E dot dA is integration of E dA cosine theta. Now, if you try and choose an arbitrary Gaussian surface, no matter how you choose it, for an arbitrary charge distribution that has no symmetry, you're not guaranteed that this cosine of the angle between the electric field and area vector is going to be the same everywhere. And certainly it won't necessarily be equal to, the angle won't necessarily be equal to 0. So you're going to have a problem with the cosine. You won't be able to get rid of the cosine in the problem. It's going to remain in the problem in the integration. Also, if you evaluate the electric field, the magnitude at different points on the surface, it's not necessary that it'll be the same value. So again, you're stuck. You won't be able to take the electric field outside of the integration. So in general, for arbitrary kind of charge distributions, you won't be able to find a Gaussian surface where you can deal with the E and the cosine theta in a nice way that will allow you to get rid of the cosine and get the electric field outside of the integration. So in general, you're stuck. The equation is still valid, so Gauss's law is still correct, but you can't use it to calculate the electric field. So there are two different questions and they have different answers. The only way you can proceed to get the electric field is if you cut up your surface into different parts. Here I just put two parts, but maybe you could have many different parts. And the idea is that on some parts of the surface where the angle is 0 between the electric field and the area vectors, then the cosine theta is just 1. So I got rid of the cosine. And the electric field has to be constant everywhere on that surface, so I can take it outside of the integration. So that would deal with this kind of surface. In other parts of the surface, if you have, for instance, the angle 90 degrees between the electric field and the element of area, then the cosine 90 is 0, and this whole term would be 0 anyway. So you got rid of this term completely. So these terms will be the only ones that will survive. So you have to be able to do this for some Gaussian surface in order for you to be able to calculate the electric field. Only three kinds of symmetries where this can happen are the spherical symmetry, cylindrical symmetry, and infinite sheet symmetry. And we've done problems in the previous videos for each kind to show you how to derive the electric field. For the case of spherical symmetry, the angle between electric field and area, when you take a spherical Gaussian surface, the angle is always 0. So you cosine 0 is 1, and the electric field is constant everywhere on the surface from the symmetry, so you can take it outside of the integration. For a cylindrical symmetry problem, you cut up the surface into three parts: the top, the sides, and the bottom. For the top, the angle is 90 degrees between electric field and area, so the flux is 0. For the bottom, the angle is also 90 degrees, so you get 0. And then for the sides, the angle is 0 everywhere. And so you're able to take out the electric field and get rid of the cosine. For infinite sheet symmetry, again, we made like a pillbox Gaussian surface, and on different parts you have different behavior. On this part, the angle was 0. On this back part also the angle was 0, but on the sides the angle was 90 degrees. So you got rid of the flux on the sides. So these are the only kinds of symmetries where you can use Gauss's law to get the electric field, but it doesn't mean that Gauss's law is not valid for arbitrary charge distributions.